Hello all of you. Welcome to the 39th lecture on the course on analysis and modeling in chemical engineering. In this week, we have been discussing about graph theory. We discussed the different ideas about graphs, the definitions and so on, and how we can use graph to identify the cyclical nets inside the graph and so on. So now we will switch gears to how we can use graph theory in order to decide the priority order of solving equations. I will first begin with linear systems and then we will go for the nonlinear systems in the future classes. So let's say this is the graph, and this graph now, for example, can be for example some flow sheet for which we want to do a material balance equations, and these vertices now may refer to different units in the flow sheet, and for every unit we may have some balances on the edges, which are the flows that are coming in and going out of the units, right. So, in order to do that, what we will first do is to redefine or renumber our edges in a more intuitive manner, and we do that in the following way. For all the edges that connect two vertices, I define the edge as yij, which is going from vertex or unit I to vertex j. So, for example, y12 is going from 1 to 2, y23 is going from 2 to 3, y32 is going from 3 to 2, and so on. And then there are also some interfaces which are basically some input or output coming to a vertex. So, those interfaces I represent as yi. I do not differentiate between input and output in numbering, but that can be seen from the graph. So, yi is the input or output interface for vertex I. So, in this case we have two input interfaces. For vertex 1 we have the edge y1 corresponding to the input, and for vertex 4 we have edge y4 corresponding as the input, and similarly we have two output interfaces, y9 from vertex 9 and y10 from vertex 10. And now we can go ahead and write the balance equation for every node. Let us say, for example, this edges represent the overall mass flow rates or molar flow rates, and if there is no reaction in the case of molar flow rates, or for the overall mass, even if there is a reaction, then the same thing applies. And that now we can write in a general form for any edge, the, let us say for the edge 1, we are going to have y1 that is coming there minus y12 minus y13, the two outputs going from vertex I, and that should be equal to 0 at steady state, right. In a similar manner, we can write equations for all the vertices. Let us say for the 10th one, we have y710 minus y10 is equal to 0, right. And just if you have this kind of material balance equations, of course, it is quite simple to begin with. We can see how we can use graph theory to figure out how we can basically attack these material balance equations. Keep in mind that whatever we are doing in the class, this is for fewer vertices or units, but once these things happens on a much bigger flow sheet where we have hundreds and thousands of units or vertices, in that case the same problem becomes quite complicated, right. But whatever principles that we will discuss, that actually is designed for large flow sheets, but we will show applications only for small flow sheets. Okay. So, we can, for example, begin with doing the Boolean matrix for this particular graph. For the Boolean matrix, as you may recall, the interfaces are not considered. So, we do not consider y1, y4, y9 and y10, And the Boolean matrix, the rows basically represent where from is coming, and 2 represents where to it is going, right. So, let us say in this case, starting from vertex 1, we can go to vertex 2, and therefore, I put a 1 there because we have a is y12 going from 1 to 2. Similarly, I can go to 3, and that is all I can go in one step. From 2, I can go to 3 in one step. From 3, I can either go to 2 or I can go to 6. From 4, I can only go to 5, and from 5, I can only go to 6, and from 6, I can go to 7, and from 7, I can either go to 8 or to 10, and from 8, I can either go to 6 or 9, and from 9, this is the output interface. So, from 9 we cannot go anywhere, and from 10 also we cannot go anywhere, right. So, first start with the Boolean matrix for this graph, and then we can also go ahead and do the reachability matrix. The more formal way of doing it is to basically compute R star as R plus R square plus R cube plus so on. We will keep on doing the sum until it becomes like a constant, or in terms of the Boolean sum, we have said when Bn becomes equal to Bn plus 1. For acyclic graphs, we will see that the higher powers of R will vanish, and for cyclic graph, we see that it becomes kind of periodic, right. But nonetheless, this R star will actually converge to some value, and that is the reachability matrix we have defined, right. But for this particular case, I will do the reachability matrix purely by inspection, by seeing that where all I can go from a vertex to another vertex in like as many steps. It does not matter how many steps we are taking for the reachability matrix. So, from 1, I can clearly go downstream to 2 to 3, but there is no way I can go to 4 and 5. So, I can go to 2, I can go to 3, I can go to 3 in 2 steps, I can go to 2 in 1 step, but for R star it does not matter. 4 and 5 I cannot clearly go because that would mean a backward movement on an edge, that is not possible. It is a directed graph. And I can of course come down to 6, and from 6 I can then access 7, 8, 9 and 10. So, this is all the vertices I can go from 1. I cannot come back to 1. Keep in mind here that this y13, it is a bypass stream, it is not a recycle. Had this S been reversed, then I could have come back to 1, but this S is a bypass, so I cannot come back to 1. Now, from 2, similarly, we can go to 3, and in fact, from 3 I can come back to 2. So, I can also go from 2 to 2 in 2 steps. I cannot come to 1, but I can come to 6 and then all the downstream vertices 7, 8, 9, 10. From 3 again I can come to 2 and 3, and I can come to 6, 7, 8, 9, 10. From 4 I can go to 5 and then 6 and then all the vertices downstream, but there is no way I can come to 1, 2, 3 starting from 4. From 5 I can go to 6 and all the downstream vertices, but I cannot come back to 4 and also 1, 2, 3. From 6 I can come back to 6 because there is a loop 6 to 7, 7 to 8 and then 8 to 6. So, I can come back to 6. I cannot of course come back to 1, 2, 3 or 5, 1, 2, 3, 4, 5. So, we have 6, 7, 8, 9, 10, and from 7 again because it is forming a loop here, cyclical net here. So, I can come back to 6 and therefore, 7, 8, 9, 10, and from 8 again it is part of the same loop. So, I can come back to 6, 7, 8, 9, 10, and from 9 I cannot go anywhere irrespective of the number of steps because it's an output interface, and from 10 as well I cannot go anywhere. So, if you see again, I can do a formal computation of cyclical nets by doing something like star intersection R star transpose, and that is the way it will be done in a program, computer program. But in this case, we can see it by inspection that there are two cyclical nets in the graph. One is between 2 and 3, that is a order 2 cyclical net, and other one between 6 to 8, 6, 7, 8, that is also a cyclical net of order 3. And in fact, they do not share any common vertex, and therefore, both can be considered maximal. None of them is subset of each other, and they are not sharing a common node. So, therefore, both are maximal cyclical nets, and therefore, what this means is these guys need to be solved simultaneously. So, we have identified from here that there is a pair of vertex 2, 3, and there is a triplet of vertices 6, 7, 8. So, these guys cannot be solved alone, they need to be solved together, 2, 3 together and 6, 7, 8 together, right. Apart from this, all the other vertices are not a part of a cyclical net, and therefore, probably they can be solved alone, right. So, based on this, we develop a decomposition scheme and set the priority order of solving this graph, right. So, before we get there, we have a proper way of writing the balance equations by the incidence matrix for this graph, right. So, how do we do it? So, as we have discussed earlier, for the edges, that is along the columns in the incidence matrix, we will put a -1 if it is an outgoing S, and +1 if it is an incoming S, and 0 if it is not connected to the vertex, right. So, y12, and now it is, you can see, very intuitive from the labeling that we have done. So, we have defined the label as yij is something that is going from vertex I to vertex j. So, therefore, yij becomes the outgoing at I, and therefore, for I will put a -1, and it is going to vertex j. So, for j I will put a +1, right. So, for y12, therefore, I put a -1 for 1 and +1 for 2. For y13, -1 for 1, +1 for 3. For y23, similarly, -1 for 2, +1 for 3. For y32, -1 for 3, +1 for 2. For y36, -1 for 3, +1 for 6. For y45, -1 for 4, +1 for 5. For y56, -1 for 5, +1 for 6. Similarly, for y67, -1 for 6, +1 for 7, and y78, -1 from 7, +1 at 8. For y710, -1 for 7, +1 for 10. For y86, -1 for 8 and +1 for 6, and y89, -1 for 8 and +1 for 9. And next thing what I will do is I can also define the augmented incidence matrix, which will have all the columns which are present in the incidence matrix and the rows, but we have additional columns corresponding to the interfaces. So, for the interfaces, for example, y1 is an input interface which is +1 at 1, y4 is an input interface which is +1 at 4, y9 is an output interface, so it is -1 at 9, and y10 similarly is -1 for row 10. And now, once we have that, then as we have discussed, we can define a column vector y for the edges, and then doing this multiplication of the augmented matrix what we have obtained with this column vector y, we can get the balance equation for this case formally, but in this case we can also do it by inspection. So, for vertex 1, you can see it is y1 minus y12 minus y13 is equal to 0. For vertex 2, we are going to have y12 plus y32. There are two incoming edges, minus 1 outgoing is y23 is equal to 0. So, you can see y12 is coming there, y32 is coming there, and y23 is a leaving edge from there. From 3, we have y13 and y23 are the two incoming edges, and y32 and y36 are the two outgoing edges. For 4, we have y4 minus y45 equal to 0. For 5, I have y45 minus y56 is equal to 0. And for 6, we have the incoming edges, actually 3 of them, y36, y56 and y86. So, I write all the 3. And then we have one outgoing is y67. And for 7, we have one incoming is y67 and two outgoing is y78 and y710. And for 8, we have one incoming is y78 and two outgoing is y86 and y89. And for 9, we have one incoming is y89 and one outgoing is y9. And for 10, similarly, y710 is incoming and y10 is outgoing. Okay, keep in mind this 1 to 10 what I have written, these are the labels, they are not part of the matrix. So, A dot y is equal to the null vector gives me the balance equation. So, we have a programming way in which I can analyze a graph starting from the incidence matrix and augmented incidence matrix, multiplying with the column vector, which in this case are the flow rates, let us say the mass flow rates, and we can get essentially the mass balance equation for all the units in the flow sheet. So, now we have these 10 equations and we want to see like which one to attack first, right. I already have seen that there are two cyclical nets which has to be done simultaneously, but can we set an order of which equation to begin with and then do what and then do what, which will help me develop a program for this. Of course, keep in mind that some part of it also depends on what is given to you. In this case, for example, you have 10 vertices. So, essentially you have 10 equations that you can see here, and then you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 edges. So, we have 16 variables. So, the degree of freedom in this case is 6, 16 minus 10. So, it will also depend on what variables are specified to you, but what this priority order setting may also help you in addition to providing you the solution scheme is to tell you also which of these variables should be specified, or if they are specified then the equations are simpler to solve for, right. So, this is one other advantage we see from the graph theory and we will take examples of that later. Okay. So, the first step in our decomposition scheme is the following. So, we look at this R matrix and we look at the vertices which has no ancestors. Let me quickly populate my R matrix here. So, from 1 I can go to 2 and 3, from 2 I can go to 3, and from 3 I can go to 2 and 6, and for 4 I can go to 5. From 5 I can go to 6. I'm essentially repeating the steps whatever I have done. From 6 I can go to 7. From 7 I can go to 8 and 10, and from 8 I can go to 6 and 9, and from 9 and 10 I cannot go anywhere. So, what we notice here in this R matrix, there are two columns that contain all zeros. And what do the columns represent? So, columns represent where to I am going. So, in other words, if I look along the columns for the vertex 1, let us say, it represents all the ancestors of 1. And similarly, if I look along any of the rows, this gives me all the descendants of, let us say, 10 in this case, right. So, now we have a way that we can look along the columns and figure out what is coming after 1 in one step, and that is what is coming before 1 in one step, and the descendants that will come along the row, which will tell me what is coming after 1 in one step, right. So, we will first look for columns containing all zeros, which therefore means that these are the vertices without any ancestors, nothing comes before this, as is very much apparent here. So, we for our matrix we are not considering these interfaces anyway. So, for 1 nothing comes before this, I cannot reach 1 from any other vertex, right. Similarly, 4 I cannot reach to vertex 4 from any other vertex in one step, in fact any number of steps, right. So, therefore, we can solve the balances for these vertices first. Whatever balance equation we have for these vertices, that is the first equation and the fourth equation, I should solve first, because they do not depend on any other vertex in the graph, right. So, this becomes the first step in my process, that I identify the columns containing all zeros, and whatever edges, whatever vertex these columns correspond to, the balance equations for those vertices are going to be solved first. And they need not be done simultaneously, because 1 and 4 are not dependent on each other. So, we solve 1 or solve 4 in any order. So, the way I have written is solve 1 and solve 4, but they can be done pretty much in any order. So, once we have figured that out, that 1 and 4 does not have any ancestors, and therefore 1 and 4 balances has to be done first. Now, what I will do is basically delete those vertices and all the edges that starts from those vertices or coming to those vertices in the graph, right. So, you see here I have a cross sign. So, as soon as we figure out that 1 and 4 has to be done together, I basically delete y12, y1 is already not being considered. I delete y12, I delete y13, and I also delete the vertex 1. Similarly, I delete y4, the y4 is already not being considered. I delete the vertex 4 and I delete the edge y4, 5. So, only the remaining vertices and all the edges connecting them becomes the reduced graph that we have. What this amounts to is basically deleting the rows and columns. I am showing in the yellow here, the rows and columns corresponding to the units 1 and 4 or vertex 1 and 4 in the flow sheet. And I am now left with the vertices 2, 3, 5, 6, 7, 8, 9, 10. So, if we do that, now we have this reduced graph and the corresponding Boolean matrix again I can populate. So, from 2 I can go to 3. Of course, I have the matrix done before, but just for demonstration I am doing it again. So, from 2 I can go to 3, from 3 I can go to 2 and 6, and from 5 I can go to 6, from 6 I can go to 7, from 7 I can go to 8 and 10, and from 8 I can go to 6 and 9, and from 9 and 10 I cannot go anywhere. And now we see again are there now any vertex that contains no ancestors? That means I again look along the columns containing all zeros. Keep in mind that the column corresponding to vertex 5 was not earlier all zeros, right? So, in the earlier step, when I was doing this 5 was having an ancestor in 4, right? But since we have deleted the vertex 1 and 4, so now that column corresponding to vertex 5 has also become all 0, right? In fact, I can do it again, but you can see it here as well that this is all zeros, right? So, now I can solve the balance for vertex 5 first, but already we have figured out that 1 and 4 has to be solved first, right. So, this column became all 0 only after deleting the rows and columns corresponding to vertex 1 and 4. So, therefore, I will solve the balance for 5 after I am done with solving the balance of 1 and 4. In general, we are going to solve the equations for these vertices first, but after the previously identified firsts. So, we already have figured out 1 and 4 has to be done first, that remains the initial step, and then in the next step I will solve for the balance of 5. And again I do the same thing, again I delete the vertex corresponding and the edge corresponding to that vertex. So, I delete 5 and I delete y 5 6 from the graph, and I also delete the row and column corresponding to vertex 5 from the graph. And now I have a reduced graph containing only 2, 3, 6, 7, 8, 9, 10. Let me again populate the R matrix for this case. So, from 2 I can go to 3, from 3 I can go to 2 and 6, from 6 I can go to 7, from 7 I can go to 8 and 10, from 8 I can go to 6 and 9, and from 9 and 10 I cannot go anywhere. And then I again repeat the same step. And now we see that in this particular case, now there are no columns containing all zeros, right. So, once that happens, then we move to the next step of our algorithm. So, we can see here that now we have no column containing all zeros. So, now we can move to the next step. And what we do in the next step is now we look for the rows containing all zeros. These are the vertices without any descendants. What does that mean? That of course, there is an edge coming from other vertex to this vertex, but nothing goes out of there, right. So, just because we have done the vertices with no ancestors first, in a similar way we can do these vertices in the end, because nothing depends on them. Their balances depend on the other vertices, but no other balances depend on them in that sense, right. So, therefore, if there is a rows containing all 0, then we can basically solve those balances last, right. So, I have therefore kept this in the last. I have still not figured out the intermediate step, but 9 and 10 balances again in any order can be done towards the end, right. So, we again delete the vertex 9 and 10 and the edges corresponding to these vertices, and now I am left with basically the vertex 2, 3, 6, 7, 8, which essentially are the cyclical nets remaining in the graph, right. But as a matter of practice, we always go back to the previous step, that is the first step, that is we identify columns containing all zeros and then rows containing all zeros. It may so happen that after reduction until here, let us say after deleting rows, we may now have a vertex for which we have no ancestors. So, those balances again has to be done first, right. So, always we go back to the step 1 of algorithm, look for columns containing all zeros, then the rows containing all zeros, and then only we proceed further, right. So, let us see here. So, we have 2, 3, 6, 7, 8. Let me do the Boolean matrix quickly. From 2 I can go to 3, from 3 I can go to 2 and 6, and from 6 I can go to 7. From 7, I can go to 8, and from 8, I can go to 6. So, now we are basically reduced the graph to the graph containing only cyclical net, as you can see here, and therefore now we have to see with cyclical net. So, we have two cyclical net here, has to be done first in the graph, right. So, in the next class we will discuss how to go further from this particular point in the decomposition of linear system. So, with that I stop here. Thank you so much.